Unit Overview. In this unit, we turn to the topic of algorithm. The unit begins with formal definition of an algorithm. It then describes different applications of algorithm in various disciplines. It also provides details of different techniques used for the analysis of algorithms. Objectives. After completing the unit, you should be able to understand the meaning of an algorithm, describe various formal applications of algorithms, distinguish between empirical and analytical method for analyzing algorithm, understand the use of big O notation for expressing the performance of an algorithm in terms of time and space utilization, learn rules for specifying the behavior of algorithm for large data inputs. Introduction. An algorithm is a step-by-step procedure for solving a problem. This is a notion generally applicable to problems encountered in real life. A cooking recipe, for instance, might be designated as an algorithm. However, in computer sciences, algorithm has a special meaning. Formally, it is defined as a step-by-step procedure with the following characteristics. Number 1. It must have some important data to operate on it. Number 2. It must produce at least one result. Number 3. It must terminate after a finite number of steps. Algorithms have long and fascinating history. The step-by-step procedures for solving geometrical and arithmetical problems can be traced back to the ancient Greeks over 1,000 years ago. An efficient method for finding the greatest common divisor of two integers was proposed by Euclid. However, first systematic procedures for performing arithmetic were studied in 50 AD and recorded in an Arabic textbook by the famous Persian mathematician Al-Khwarizm. The word algorithm is, in fact, derived from the name Al-Khwarizm. Algorithm. With the advent of computers in recent years, need of appropriate algorithm for solving a variety of problems has sharply arisen. Some common types of algorithm and their uses are: searching algorithms are designed to search for a given data value in a massive data collections. Sorting algorithms are commonly used in computer applications to arrange data items according to user-specified criteria. Compression algorithms are meant to reduce the size of data and program file for their efficient exchange over the networks. These are also used for compression of image, audio, and video data. Fast Fourier transform is extensively used in digital signal processing. Encoding algorithms are used for encryption of data in secure transmission and exchange of sensitive data. Geometric algorithms are useful for identification of geometric shapes. Pattern matching algorithms are meant for comparing images and shapes. Parsing algorithms are designed to identify different programming constructs by the compilers. Classification of algorithms. Depending upon the strategy for solving a particular class of problems, algorithms are classified as iterative, divide and conquer, greedy, and backtracking. In iterative algorithm, certain steps are repeated in loops until the goal is achieved. Iterative algorithms are used commonly for sorting of small sets of data. In divide and conquer algorithm, a given problem is fragmented into smaller subproblems. The subproblem is then partially solved. The algorithm is recursively used over several parts and terminated when further subdivision cannot be continued. The divide and conquer algorithms are frequently used for searching and sorting problems. The greedy algorithms work on the principle that an immediately available best solution at each step must be chosen without worrying about its effect on subsequent steps. For example, if we want to give change for 73 rupees in minimum number of currency notes, the immediate best solution would be to start with the highest denomination, that is, a 50 rupee note, then two 10 rupee notes, then 2 rupee note, and finally 1 rupee note. The greedy algorithms are useful for solving scheduling and graph theory problems. In backtrack algorithm, all possible options are examined by moving back and forth until the solution is found. These kinds of algorithms are useful in graph theory. Two common approaches are depth first search (DFS) and breadth search first (BSF) algorithms. Specification of algorithm. As we mentioned earlier, algorithms play a central role in manipulation of data structures used in any program. In order to code the underlying procedures, it is sometimes useful to describe the algorithm in human-readable form using either natural language or pseudocode. Use of natural language. In natural language, we can use words and phrases to describe the procedure and computational steps. For example, words like read, write, compute, set may work for input, output, computations, and assigning values to a variable. Likewise, arithmetical operations can be expressed using words like add, subtract, divide, and multiply. The word repeat may be employed to express loop structure. For example, the Euclid's algorithm for finding the common divisor of two positive integers can be expressed in natural languages as shown. The algorithm is used on the observation that common divisor of two integers is also the common divisor of the difference. Use of pseudocode. The description of an algorithm in natural language tends to be wordy and verbose. Sometimes it does not clearly define and may even be ambiguous. Pseudocodes provide an alternative and better way of expressing algorithms. Pseudocodes, as the name implies, is a mixture of natural language and high-level programming notation. Although there is no standard format for writing pseudocode, the following notations are commonly used. Identification. Each algorithm is assigned a name and some identification number. Comments. Comments are optional and enclosed in square brackets. Variable names. These are expressed in capital letters. Assignment. A left arrow indicates assignment statement. Operators. Arithmetic and logical operators are identified with mathematical symbols. Input and output. The I/O operations are shown with words read and write followed by variable names or output message. Control structure. Logical steps are expressed by using the phrase if then else. Loops. The repetitive operations are described by the word repeat, that is followed by loop structure described in terms of for or while statements. Specification of algorithm. The Euclid's algorithm for the GCD can be expressed in pseudocode as shown. The pseudocode is not only human readable, it can also be easily translated into a high-level programming code fragment. C++ code for the GCD algorithm is algorithm analysis. The performance of an algorithm is measured in terms of runtime and storage requirement as a function of input size. An algorithm that provides a correct result but takes enormously long time is not very useful. It is, for instance, of little help in real-time problems which require solution in split seconds. Likewise, an algorithm whose storage requirement increases rapidly with the input size is not amenable to implementation on small computers. Furthermore, there may be trade-off between time and space requirements. Thus, both time and space analysis is of crucial importance in judging the efficiency of an algorithm. The time analysis uses various techniques to estimate the runtime of an algorithm for a set of input values. Basically, two approaches are adopted which are classified as empirical and analytical. Empirical analysis. In empirical method, the runtime of an algorithm is measured in real time for different sets of input values. The actual time is plotted against the input size to analyze the growth rate. Figure also shows a time measurements of two algorithms for sorting. The empirical approach has several limitations. It essentially depends on the computing environment such as hardware and operating system. Thus, the result of analysis can vary with platforms. It also depends on the data set chosen for test purposes. The empirical data may not be comprehensive, covering all possibilities. To a greater extent, runtime depends on how efficient the algorithm is programmed for a particular machine. Analytical analysis. The analytical method uses mathematical techniques to estimate the runtime. The method identifies crucial operations in an algorithm that contribute significantly to the overall processing time. The number of key operations can be determined by analyzing the pseudocode for the algorithm. Let us consider the algorithm for finding the largest value in array A of size n. The pseudocode is shown in the figure. Step 1 defines a temporary variable max, which is assigned the first element A of 1 of the array. Step 2 and Step 3 compare other elements A of 2, A of 3 to A of n with max. When an element greater than max is encountered, the value of max is replaced with current element. Thus, at the end of loop, max would contain the largest array element. By inspecting the pseudocode, we draw the following conclusions. Step 1 involves one access of array element. Step 2 makes n-1 assignments to variable j. Step 3 retrieves an element n-1 times and makes n-1 comparisons. Step 4 retrieves an element n-1 times and makes at most n-1 comparisons in worst case, assuming that last element is the maximum element. Thus, total runtime for the algorithm is as shown. An important point to bear in mind is that algorithm analysis is not concerned with determining the runtime for a particular value of input. Rather, the analysis is carried out for the entire range of allowed values. Algorithm growth rates. In many cases, we would like to know how the runtime of an algorithm varies with the variation in input size. For example, we might need to know how the sorting time would grow with the increase from 1,000 to 1,000,000 items. The behavior of an algorithm, say, for very large input size is often called asymptotic analysis. In the previous example, we noted that the runtime for max algorithm varies as kn plus c, where k and c are constant, n is input size. For large values of n, the constants would become insignificant. Thus, we can say that asymptotically the runtime of Mach's algorithm varies as n. In other words, the execution time is proportional to n. The big O notation. If the runtime of an algorithm varies in proportion to the function f of n, algorithm is said to be of order f of n. In short notation, this is expressed as O f of n. The function f of n is called growth rate function or complexity of the algorithm. Because capital O is used to express the growth rate, it is called big O notation. Thus, if runtime varies in direct proportion to n square, we say that complexity of algorithm is O of n square. Algorithm growth functions. This table shows some of functions commonly used to study the behavior of algorithms. The graph and functions commonly used in analysis of algorithms are shown on the screen. Logarithmic algorithm. The growth function has some useful properties which reflect performance characteristics of an application. The runtime of a logarithmic algorithm varies as log n, where n is size of problem. Conventionally, log has base 2. Logarithmic algorithm grows slowly and has the best performance. For example, if the problem size increases by a factor of 1000, the runtime increases roughly by 10. Binary search algorithm has logarithmic behavior. Linear algorithm. The execution time of a linear algorithm grows in direct proportion to the size of a problem. The performance of a linear algorithm is rated as good. An algorithm based on a single loop shows linear growth rate. Examples of linear algorithms are searching, deleting, and inserting operations on arrays and vectors. N log n. The n log n has moderately high growth rate. The divide and conquer algorithms generally exhibit this behavior. Quadratic algorithm. The quadratic algorithm grows as sequence of input size. The algorithm with a pair of nested loops shows quadratic behavior. For example, the multiplication of two n by n matrices has O n square runtime. The quadratic algorithm have fast growth rate. Cubic algorithm. The runtime of a cubic algorithm varies as the cube of the problem size. Such algorithms grow very rapidly. A problem involving 3 nested loops has a cubic growth rate. Operations on 3-dimensional arrays, for example, exhibit cubic behavior. Exponential algorithm. The algorithm with runtime of the order of 2 power n, where n is input size, are called exponential algorithm. These algorithms grow at extremely high rate and not very useful for many practical applications. Below is a comparison of growth rates of main functions used to analyze the algorithms. The big O rules. We have seen that big O notation provides a convenient method for expressing the asymptotic behavior of an algorithm. When the input size becomes very large, we can simplify the big O representations using the following rules. Addition constants may be ignored. For example, obviously, constant 100 would lose its significance when n becomes very large. Lower order terms may be dropped in favor of higher order terms. For example, the simplification is based on the observation that smaller order do not contribute as much to the runtime as higher order terms. The multiplication constant may be ignored. For example, this simplification is based on the observation that in analyzing an algorithm, we are interested only in relative growth rate rather than absolute. This is shown in the graph. In-depth runtime analysis. So far, we have examined the asymptotic behavior of an algorithm. Sometimes it is useful to have an estimate of minimum, average, and maximum runtime. These possibilities are referred to as best case, average case, and worst case. Best case analysis. Best case analysis is meant to determine the minimum runtime of an algorithm. The execution time, of course, depends on the nature of input data. One or more of the inputs may result in the shortest time. For example, in a searching problem, the most favorable input would be the input value which matches the very first item in the list. In a sorting problem, the best case would be when the items in a list are already in sorted order. Best case analysis, though informative, has little practical value because in solving a problem, we are often more interested in knowing the maximum time required for the solution. Worst case analysis. In worst case analysis, the maximum runtime is determined by considering the most unfavorable input. For example, in a searching problem, we determine the maximum search time by assuming that the item to be searched would occur at the end of a list. Thus, worst case analysis yields the most pessimistic time estimate. It provides the upper bound in the runtime and guarantees that in all circumstances the runtime would never exceed this limit. For such reasons, algorithm analysis is most often done on worst case basis for most unfavorable inputs. Average case analysis. The average case analysis is done to find the average runtime of an algorithm. Quite obviously, the average time lies somewhere in between the optimistic and pessimistic time. For example, in searching problems, the average time would be the runtime when the input values lie somewhere in the middle of a list. For most problems, however, an average time can be determined by considering a distribution of input data over the entire range of admissible values. Such an analysis relies on probability theory. In general, average case analysis is more complex. Space analysis. This space analysis is concerned with determining the maximum storage requirement needed for an algorithm. The analysis, in essence, estimates the number of bytes as function of input size. Since variable and constants occupy fixed amount of storage which do not depend on the size of problem, thus space required is expressed as O of 1. The space requirement for complex data structure is estimated by counting the number of bytes for each data item. For example, an array of integer of size n would require 4n bytes, assuming that an integer requires 4 bytes. Thus, the space complexity of the array is O of n. In some cases, there may be trade-off between runtime and storage requirement. An algorithm with small runtime may require large storage space. For example, sorting of a large data file stored on secondary storage can be performed more effectively in shorter time by using a very large memory space in the main storage of a computer.